Professor Alan Haungs, Physics 124, the Ray Tracing Lab. This is part 3. Involves using a convex lens. What I'm using, though, instead is what's called a Fresnel lens, which is going to function the same way. It just gives me more area to work with. It's easier to work with. Look up the word Fresnel lens if you want to know how that's different. I'll show it off to you later, but it has the same function. Okay, so what we're going to do is we're going to see or determine what does this observer over here, what do they see? What does their eye see if a lens, convex lens, is placed here with an object here that's closer than the focal point? So first we'll just, for the sake of the exercise, determine where the focal point of this lens is. So what they would have you do in the lab is you take a parallel ray, head directly parallel towards the, so I'll try to get a parallel ray as best I can. Okay. Make it as accurate as I can. Okay. That's not perfectly accurate, but you can see it's pretty good. Where does it intersect the optical axis? I'd say right about there. Right about there. Let's try it off of a different, let's try a different parallel ray, see if we end up with the same spot. We won't, I know we won't, because it's never totally precise. The lens isn't perfectly flat. You know, I'm using my hand here, I'm not using machinery. So it's going to be close, but not, well, that's pretty off. That's awful close. Okay. That's your focal point. So that was pretty close. I was kind of surprised it was that close. Maybe my hand is better than I thought it was. Okay. That's almost like about, it's almost 10 inches, the focal length. And we're maybe about 3.5 inches. So the focal point also goes this way, 10 inches. Okay, so we're within that range. So we want to know, this is how you typically would use a magnifying glass anyway, right? You'd have your face about this far from it, maybe, about almost half an arm's length, and you'd be looking at something this close. So that's kind of a reasonable way to use it. So I'll call that the focal. That's your focal point. That's just, okay. Now I haven't been using the principal rays as the book recommends. I've been doing a little bit more freestyle here. But the principal rays is a good way to do it also. Okay, so I'm going to say that there's going to be a beam of light that's going to come off that little T part right there. We've done this a million times. So I'm going to trace it. So we're going to start with the bottom. So I'll give it kind of a dramatic. We'll go dramatic. So it's coming off of here. It's hitting the lens. And then it begins to take a different path. So it takes this path. Okay. Okay. There. We'll call that the base. 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 Then we'll do another one of the base. We'll do another one. So we're going to find out, where is this image? Where do these rays converge? That's what we want to know. Where do they converge? Where does the person perceive them coming from? I better not go that steep. Let's see here. There we go. I'm only drawing the ones that are going through the lens. I don't want to take the time to draw everything else. It just takes more time. This is the important part of the information. Okay, so that's a base. That's a base. Okay. Now let's do the tip of the arrow. Okay. We'll do a similar kind of trick here. You should be able to do this in your sleep now. I'm going through the tip of the arrow. Starts about here. Goes about here. I could say maybe here. Okay, so that's a tip. That's the tip. Okay, we'll do another one, different angle. Okay. Off the tip. There's a tip. There's a tip right there. Okay. Okay. Now I'll show you the lens. This is what the lens looks like. That's it. It's thin. It has these little grooves cut in it at an angle. Uses Snell's law to accomplish the same thing, other than the fact that what it does is it creates a little bit of a, I don't know, what would you call that? A artifact. Those lines are an artifact, an optical artifact that you may or may not care about, but you can see what a wonderful device that is, right? Okay, now let's trace it back and see where this eyeball thinks this image is. Okay. Now remember, when things converge, when the light converges, that's where it's believed it came from, because it was diverging from this or this point or this point. So, and the eye over here only perceives the light that's coming toward it. So this eye could be here, 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 and all these different locations. So this is just showing the eye in principle looking in that direction, not necessarily in that exact spot. Okay. Okay. Do the same thing over here. Okay, converges right there. Okay. So with the base. This will never be perfect, but it sure will show you in principle how this works. You'd have to be much more careful to get a perfect one. I'm just doing this very quickly. Okay. Okay. So, not too bad. Again, like I said, not perfect. So the tip of the arrow is here. And the T of the base is here. So it's exactly as you would expect. It's larger. It magnified it. And that's the experiment as they wanted you to do it, except the only thing I did differently, I didn't use pins. I just took a U-clamp and did a little machining. Did some machining so I could put my little laser pointer in there, and all I was doing during these experiments was just rocking the laser to get a straight line. So, because I couldn't picture myself standing in front of the camera with my eyes lining up pins and everything. That probably wasn't going to work. So I'll give you some more things. I'll give you something to do and some questions to answer. And I hope this has been very enjoyable and educational to you.